All right, guys, 6500 logistic regression, nearing the end. Probably going to be 3 more videos, maybe, I'm not sure. Anyway, the attention in this video switches to having several B sub k's, and we get into what's something called the likelihood ratio test. So, I guess what we want to do here is take a look to see if adding a variable actually increases or provides an improvement over the original model. And we essentially do this with every model, because we look at a particular model that we create and we compare it to the null model to see if it's an improvement. But we're going to get into a little bit more structure with the process. So anyway, what I want you to do, there's a a data set on posted on Blackboard. It's called Logistic 6. You can see that I've already loaded it into R, and you can see this is handy to make sure that you have the correct data set. So I don't really know what x1, x2, x3, x4 are. Y is our dependent variable, coded zeros and ones, so logistic regression techniques are appropriate. And of course the first is just the ID, which is not worth much yet. So if we were going to take a look at a model, let's just create a model with maybe well, I don't know. I'll tell you what. Let's just do the full model. I'm really kind of shooting from the hips here. I have no notes at all, but I know what I want to accomplish here. So I want y as a function of x1 plus x2 plus x3 plus x4 in family equal binomial. All right. And the next thing I want to do is I want to create my null model. Wow, there's been a lot easier way to do this. And this is kind of redundant because you get what I want to accomplish here just by looking at the null deviance. But let's go on so I can actually implement the likelihood ratio test and make a determination. So if I were to compare these models, in other words, is the full model that I'm working with an improvement over the null model? So what I would do is I would look at the ANOVA over my initial model, the second model, and I would use the chi-square procedure. And what I end up getting here is I end up getting a deviance of 21.264, degrees of freedom 4, and I get a p-value of 0.002. Now, does that mean that we have an improvement over the null model? Well, I don't know. Let's go ahead and look at some stuff, because we're going to get into a formal presentation of null hypotheses and should x1 or something be deleted from the model. So we'll see how it all plays out. So what I want to do now is I want to address with a ton of structure, should we drop x1 from the model? Well, in other words, what we're testing here is we are testing is beta 1, again, corresponding with x1, equal to 0. Beta 1 not equal to 0. Now clearly, if beta 1, if we can't reject this statement, then we can eliminate x1 from the model, because we can't reject the fact that, or the claim at least, that the the coefficient is equal to 0. But if we end up with a significant result where we end up kind of quote unquote accepting the alternative hypothesis, then we're concluding that our beta 1 is not equal to 0, so it should be retained. So what I would want to do here is I would want to create a second model. So I'm going to go up and get my full model, but I want to subtract or delete x1, and I'm going to call this full model 2. Now, I want to run the ANOVA, and again, what I'm running here is called the likelihood ratio test. We're just doing it using R, using technology, instead of the long way. So I would put in the first model, which would be the full model. Now, we're going to get into something kind of interesting here, but I'll explain. All right. Now, what's interesting there is you notice that we get a negative deviance. It doesn't change the fact that we have a statistically significant result, and it's kind of compensated by the fact that we get a degree of freedom -1. Now, guys, obviously, if that kind of stuff bugs you, which it would me, what we would want to do is we'd want to put our smallest model first and our largest model second. So anyway, most importantly, what we would say here is we would say that our G squared, which is the test statistic for the likelihood ratio test, is 5.15 with a p-value that is statistically significant at the 0.05. So what this would lead us to do is it would lead us to reject the null hypothesis, telling us that the beta 1 is not equal to 0, so it has quote unquote a significant value. So our conclusion is that x1 should not be dropped from the model. Now, gang, let's look into should we eliminate x2 and x3. So let's go back up to the full model, and let's eliminate x2 and x3, leaving just x1 and x4. And I'll call this full model 3, kind of like full metal. Reminds me of Full Metal Jacket for some reason. Alright, so we can go back to the ANOVA. Following with what we said earlier, we could put the full model 3 to make sure that our deviance is not negative. Oh, I got that completely backwards, didn't I? Oops. You know, I did. As soon as it came out of my mouth, I knew that was wrong. Alright, so we get a deviance of 3.943, and for some reason came up with the degrees of freedom -1 and did not give us our interesting. Oh, wait a minute, this is not what I wanted. I wanted the full model. So I want, yeah, I'll see what's going on. So I want the full model. Yeah, we're still going to get that issue though, aren't we? But we will get our p-value. So guys, what we get here is we get, first of all, let's add structure to this so we know exactly what we're doing. So our null hypothesis would be H sub O, that beta, would we eliminate 2 and 3? Yeah. So beta 2 equal beta 3 equals 0, and H sub A would be not all B sub K in H sub O are 0. So our test statistic here is what, 1.21. and our p-value is 0.547, leading us to not accept the null. So guys, we would feel comfortable in dropping x2 and x3. Now, what I want to get into next is going to be test for goodness of fit. So an overall model analysis, and what I want to look at here in this case would be the full model. So what? Again, now change focus to what I would call a goodness of fit test. And what you could probably think about here is think about back in the simple linear regression, multiple regression we would use adjusted R squared, but in simple linear regression we would use R squared to give an overall assessment, right, of the model. Well, that's kind of what we're doing here. So the techniques that I'm going to address here kind of pose the question. So is a logistic regression model appropriate for modeling or explaining the relationship between the predictor or set of predictors and y, which again is obviously measured as either 0 or 1. So essentially this is kind of breaking it down to ask two smaller questions. First of all, is our data monotonic? Monotonic means it's either never increasing or never decreasing. And is it sigmoidal? And sigmoidal, just think kind of an S shape. Well, not like that, but it'd be the kind of like that. So is it S shape? Guys, there's 3 or 4 of these. Pearson chi-square. There's one way of looking at an overall model fit. There's something called a deviance. This is what the output in R gives. I think most people, well, I don't even know about that either. I think a lot of people would agree that, and I never know if I'm ever saying this correctly, the Haas Lam Test goodness of fit is the one that I want to demonstrate in this video. The Haas Lam Test goodness of fit test is perfect when you have unreplicated data sets or you have data sets with very few replications. So the process is kind of interesting, really. And I'm not going to demonstrate it, but I'm going to kind of tell you the way that this actually works. The process consists of grouping the data into classes with similar fitted values. So it groups into classes, and I don't know why, but I usually try to set it with k equal 5 classes with similar fitted values. And it's actually a pretty clever process. So What I would want to do here is I would want to is look at the range from my predicted values all the way to the highest, so the fitted values. And then I would want to come in and make 5 cuts to where the sample size in N1, N2, N3, N4, and N5 were pretty close. So guys, in this situation, we have a 98, so what I would search for is about 20 in each of these cases, right? Now you're going to say 20 times 5 is 100. Okay, I'm off a little bit. So, maybe one of these is 19 and the other one's 19. But that would be something that I would actually search for. What would actually happen then is kind of cool, because you would create, in each case, you would create a 5x2 matrix. And the matrix would be that, okay, so imagine we have our classes. I'm not saying this very clearly. Again, this is a place where I should have probably had notes, but I thought I could wing it. So we have 5 classes again. I go for 5. Some people go for 10. Whatever. I search for 4 or 5. Usually 5. So then I have my pi hat interval. And I don't know. Let's say the first interval ranges from 0.3 to 0.35, whatever it may be. And then we get down from whatever the last class is. So this will be our lowest fitted, and this will be our highest fitted. Now the next thing we do is we come in and look at our y equals zeros. How many of these fell in these classes? And then we look at our y equal 1s and we find how many fell in these classes. Well, then what we do, as I said earlier, we create, if we have 5 classes, we create a 5x2 matrix. Well, this is called our observed matrix. Then we could easily create an expected matrix, create a chi-square, which would have degrees of freedom k minus 2. So in this case, we would have a chi-square degrees of freedom 3, and we would get our test statistic and our p-value accordingly. So actually kind of cool stuff in a way. Now let's carry it out for this data. So our null hypothesis would be logistic regression techniques. Are appropriate, and our H sub A would be logistic regression techniques are not appropriate. All right. First thing we want to do is we want to use something called a Haas Lam Test. But guys, to be able to use this, we have to install a new package. So install package, and I need resource selection. I'm going to choose a crayon. Guys, I choose California because I like those guys. Never met them. For some reason I claim that I like them. Now, depending on your internet connection, mine's extremely slow, so it may take a while. Now I'm going to access the library. All right, got a warning message. It's built under a different version of R. Let's see what happens. May work, may not. All right, so I'm going to create my and I want to. I'm going to look at the full model. So I'm going to. Guys, I don't remember what I called that. Let me I'm going to need that. Let me take the... So that's 1, 2, 3, 4, right? Okay. All right, cool. Now I want to... so the first thing it'll have me do is put my y. Now on my fitted value for a full model. And then we choose the number of groups. And again, guys, I always choose groups equal 5. If you choose groups equal 10, report it and go on with your life. This is fun. Don't know. All right, I'm confused. That should have nothing to do with it. Guys, I have no idea. Well, anyway, that other should have worked, but for some reason it didn't. So, guys, what we can say here is we have chi-squared degrees of freedom 3. Our test statistic is 1.66. And our p-value is 0.65. So we would fail to reject and conclude that logistic regression techniques are appropriate to describe the relationship between x1, x2, x3, and x4 and y. All right, guys, sorry about that. I don't know what happened with this whole y business, but it just is what it is. Take care.